afternoon, everybody, and welcome to our live streaming session. My name is Chrissy, and I'm the Lead Programs Officer for the National Youth Science Forum. Today, members of the Australian Army and Air Force drone racing teams will be taking over our social pages to give you a taste of the amazing content that you can experience on an NYSF Year 12 program. The team are going to take us through some drone technology and how it is used within the Defence Forces, and then they will introduce us to the exciting sport of drone racing. They're going to take us through how they build their racing drones and then show us some flying demos. Members of the team will be available throughout the session to answer questions, so please engage with us via the online chat section. We look forward to seeing your questions and hope you enjoy the session.
Good afternoon, NYSF. I'm Nick from the Air Force Drone Racing team, coming to you live from RAF Base Richmond in Sydney. My co-presenter here today is Luke, and we'll be telling you everything there is to know about drones, but not just any type of drone. These, which are racing drones. We'll be exploring all the interesting and cool tech that goes into making these able to fly, as well as showing you a bit about what these can do and why they differ from most other drones you might have seen. We've also got joining me here today, Steve and Jaden from the Air Force team, as well as Alex, who are here with me in Sydney. And we've also got Tomo joining you live from Melbourne in order to help with answering any questions you might have. If you've got any questions throughout any point during the stream, drop a comment down below and Tomo will pass them through and we'll answer them as soon as we can. And please, ask as many questions as you want. So the Army has recognised drone racing as an official sport for about 3 years, the Air Force for about 2 years, and the Navy about 6 months. So what that means is we've all got our regular day jobs, and then on the side, in the same way you might play netball, basketball, rugby, we have to fly around these cool things. So as I mentioned, we've all got our regular day jobs. I'm an electrical engineer in a program office which supports the wedge-tail aircraft, which is basically an aircraft that looks like an airliner, but with a massive radar on the back. The really cool thing about drone racing in defence is that all the considerations you have to put into designing one of these goes directly into all of that program support that I do with the wedge tail. So when we've got to look about separating antennas because of frequencies, making this as durable as possible but as easy to maintain as possible, they're the exact same principles that I apply in my day job, bringing that STEM aspect from drone racing straight into direct defence capability. I'll now hand over to Luke to talk a bit about his job and how STEM relates to that.
Yeah, thanks, Nick. All right, good afternoon to all our live viewers. Look, firstly, we're really excited to be here, having a chat to all of you out there about drone racing. As Nick said, it's our passion, it's our hobby, and it's also an approved ADF sport. So, a little bit about me. I guess you could say I started the team 12 months ago. When I first started drone racing, it was really difficult. You start flying and you think, wow, I'm no good at this. Like anything, you keep cracking on and you progress from, I guess, small drones, which we'll talk about later, called tiny whoops, right up to this size. Now, the way that this interacts with my current job, I'm an engineer and I'm here at RAF Base Richmond and I work on the 30J aircraft you see behind you. So while I'm pulling apart this drone, because I don't get to pull apart these too often, I get to learn about all aspects of STEM. I get to learn about the electronics, the programming, the materials, the design aspects. And for me as an engineer, that's pretty much all I want to do most of the time. So without further ado, I'll pass you on to the next member of our team to have a bit of a chat about what he likes about drone racing and who he is.
Hey everyone, name's Steve, pretty much as we were saying, work on the C-130Js, aircraft structural technician. What that entails is I get to pull apart, I get to play with these things, they're amazing, they're really fun. I can also switch that into the drone racing side of things because these do break. We do crash them at pretty high speeds. We can put them back together again. We play with these things. We can fix them. We go from drone racing side of things. We're good?
Yep.
From our drone racing side of things to our photography, to our search and rescue. We can muck around. We can freestyle. We can race whoops, the sims. We've got a lot of experience, a lot of fun. And yeah, I'll switch to Alex.
G'day, I'm Alex. What got me into drone racing was the sheer fact of being able to build and program these racing drones. Not only that, I also use these as a tool to capture video from a different perspective. Video. So, yeah, these drones that I'm using as such are designed purely for video to capture from different perspectives, but not only that, they can be made to race around a track. So, yeah, what I'll do, I'll hand you over to Jaden and he'll explain further. Thank you.
All right, thanks, Alex.
Good afternoon. My name is Jaden, and I'm a project engineer on the C-130J Hercules. I'm part of a team that look after the capability enhancements of the Herc here, and that makes sure that we continue to meet international standards, but also make sure it's a continually improving aircraft in its operational areas. That directly relates to drone racing if we consider the life cycle of a drone. Throughout the life cycle of the drone, there will be technological advancements, but also there may be changes to racing standards in the future. When we do that, we will have to consider these advancements in a cost-effectiveness way, a maintainability way, and also make sure that we meet those performance requirements that we want. Is it better than what we actually came from? Using these skills allows me to work on my engineering skills outside my work hour, which is, I guess, real fun. That is all from me.
And just a reminder to all our viewers out there, if you do have questions as we're going through, send them through. Our trusty assistant behind the desk will pass those questions to us and we'll make sure we get your answers hopefully as accurate as we can. Thank you.
Awesome. I'm going to take over for a second while we just change our cameras up. I'll introduce myself. I'm Dello. I'm currently controlling this live stream at the moment. A bit dangerous there. We'll see how we go. There could be some technical issues as we proceed through this Facebook and YouTube, and I think we have Twitch as well. Anyway, so I think the other camera's getting about ready, but yeah, please shoot for your questions. We have Tomo on the line. He's going to answer them, and hopefully I can interrupt these guys over here and actually get the experienced drone racers of the team to actually answer them. So should be fantastic. I'll pass over to Luke and Nick. Awesome. Let's go.
So you've heard a bit about how STEM relates to our jobs and how the skills we learn in drone racing directly relates to things that we do in defence. But why do we care about STEM, and why does defence actually really care about STEM? Well, we've got a whole bunch of shiny new platforms, both within Army, Navy and Air Force, these really, really cool bits of kit. But if we've got all these things that we don't actually know how they work or how we can improve them, then what's the point? So all of this technology and all these skills about STEM that we learn in drone racing, this is what we care about. We need to know how we use these brand new fighter jets, but also how we can continue to improve them. The tech that's involved in this covers so many different disciplines, from not only just basics about how drone flies and how aircraft fly, but also you're looking at different materials, electronics, and aerodynamics, a whole wide range of skill sets that goes into producing one of these. And this is the skill sets to draw over to the jobs like my members just talked about. Now, I'll hand over to Luke to talk a little bit about a few different types of drones that we've got on our bench here today.
Thanks, Nick. All right, so as promised, more about drones and drones themselves. So as I discussed before, I'm pretty new to the team, pushing 12 months now, which sounds like a lot of time, but when you go from someone who hasn't flown anything to trying to whip around a course at anywhere from 100 k's up an hour, it's quite a challenge. Now, hand-eye coordination is important, but perseverance is also important. So talking about where I started, so this is what we call a tiny whoop class drone. Tiny why? Because it's small. Whoop, I've got no idea, but that doesn't really matter. Part of why we want to start with something like this, as you can see, I don't know if it's easy to see there or not, but there's prop guards around each propeller. The propellers themselves are quite small, and the batteries themselves are quite small. That means a couple things. That means they're light, they're cheap, and they're much more forgiving if you do crash. Now, flying these around, they're still a lot of fun. They're still FPV, and they go pretty fast, up to about 40 k's an hour. Is that about right, Nick?
It's about 40 k's an hour.
40 k's an hour. So from not flying before at all, to flying, that's the best place to start. I guess you can move up probably ever so slightly into what we call the toothpick range, is that correct?
Yeah, it's toothpick.
Yep, toothpick. So toothpick are very similar to your tiny whoops, but the big difference you can see here is there's no prop guard around the edge there. So you are starting to talk about something that's a little bit heavier. It's more of a serious outdoor drone racer, I guess, if you could say that.
Describe it as a practice drone racer because it performs just like our big ones. You can see the arms are really, really small, and this is where it gets its name, toothpick, because the arms are about the size of a toothpick. This one here was about 80 k's an hour?
About 80 k's, yep.
Yeah.
Yep.
And so similar flight time of about 2 to 3 minutes. So moving up from there, we've got a bit of a special class which has emerged in the past 6 months that we call a Cinewoop. Basically, what we do for this is we build this so we can fly around small areas and carry a full-size GoPro to get some really, really cool footage. So this one here, it's spinning about 3-inch diameter propellers, and it's got these massive prop guards around it to keep it safe. So say we're flying around a museum like the Air Force team did recently at Fighter World in Newcastle. We're able to fly this thing around safely, but also if we want to be in close proximity to anything that's delicate, it's not going to get harmed because these props are nice and protected, but it can still do about 100 kilometers an hour if we want it to, and fly for about 5 minutes.
Cool.
So moving up from there, we've got the most popular and the most diverse style of racing drone. So this is what we call the 5-inch racing drone. So the diameter propellers is about 5 inches, and that's how we classify them usually. So this is where most people fly in. Reason for that is it gives a really, really good balance between top speed, but also acceleration. So it's got a top speed of about 150 kilometers an hour that can get from 0 to 100 in just 1.1 seconds. So awesomely powerful drone. And this one here, this is a specific racing drone. So if you notice, the arms aren't actually that thick, and you've got a pod on the top to keep everything protected. So this is designed to go around a track as quickly as we possibly can and just be really, really quick around it. Another style of drone that's quite popular is Freestyle. So this is the same size drone, 5-inch diameter propellers, but you'll notice that the arms are a lot thicker. It's not very aerodynamic. It looks basically like a brick that we strap some motors to. The reason for that is we want it to be as durable as possible. We don't really care about the weight too much because we're not trying to push that speed limit. We just want it to be really durable. So if we're flying around some trees or something like that, a 500-gram piece of drone versus a tree's probably going to win. So we really want this to be quite durable. And so this is the Freestyle, this is the racing. So moving up from here, we've got our 7-inch long-range drones. So the purpose behind these ones is to be able to fly far away and get really, really smooth footage. So one of the key differences you notice compared to a racing drones, arms a bit thicker because again we want that durability, but also the propellers are a lot larger. And also, for our key observers, you'll notice there's actually a GPS on this one. None of the previous drones had any GPS, so they had no idea where they were. It was all up to the pilots to sort of work out where they are and how to get home. This one here is just in case something goes wrong, we know where it is, so we can pick it up if it crashes. This one has a flight time of about 15 minutes on a good battery, compared to about the 5 to 3 minute mark on the 5-inch racing drones. So these are designed to be really, really slow. Most of them cruise at about 80 kilometers an hour, can probably still get up to the 150 kilometer an hour mark, but that's not really what they're built for. They're built for that slower, cruisier style. Put a GoPro on the top there to get some really, really cool footage. So if you've seen any of our videos from flying around tanks or anything like that, we've been using something like this, because that way we've got heaps of time to get that really, really cool footage.
Awesome.
Now,
So I'm just going to ask a quick question here. So we have, how do you hone your reflex skills to steer drones at that speed? That's a really good question, Nick. Could we answer that?
We're talking reflex skills, is
Yeah,
that right?
reflex skills. I'm pretty sure I don't have too much reflex skills, but what about you pilots up there?
Well, I can take that question and I'll let Nick jump in. I guess, as I said, I'm pretty new, and at the start, it's like anything. Your reflex skills are, a lot of it's natural. A lot of it you have to think about. So part of what we try to teach people when they first get flying is start simple, start hovering, all right? Once you can hover, eventually your reflex skills actually allow yourself to keep that quad stable. Once you learn that, it's then progressing to the next step. Okay, can I then go around an obstacle and come back? And what starts happening is your fine motor skills start adjusting to the micro movements of the quad, to a point where you're looking through the quad, through the FPV, through your goggles, and you're seeing where you need to go. And eventually what starts happening is you start getting better control of that. And a lot of that becomes automatic, I guess you could say. So really what you start trying to achieve is, okay, well, it's like a racing game, you know, like Forza, something like that. Okay, I can drift around this corner. Maybe I'm going to try to hit that corner a bit faster and then do a sharp hairpin afterwards. So you just go incrementally, step by step. Like I said, you start off, it's like riding a bike. You fall off straight away. Eventually get to that point where your reflex skills just become autonomous, really, I guess.
Yeah.
Yep.
So the best comparison I'd give to it, so a lot of what we do is sort of flipping around and holding upside down. So if you think about it like when you're trying to shoot a basketball for the first time into a hoop, you've got no idea how much force you need to apply to actually get it up there, or kicking a footy or anything like that. Exactly the same thing with this. The first time you try and flip a drone around, you end up here, here, everywhere. But eventually you get the feel for it and it becomes into that muscle memory piece. So those top pilots who are competing internationally, they're barely even thinking about what they're doing. To them, it's just that automatic reflex that Luke was saying. Hope that answers your question. So moving on, you will notice behind us we've got two very, very large drones. We'll go and pick one up. So this very intimidating piece of equipment is what we call an X-Class. This thing can do speeds of up to 250 kilometers per hour and weighs, with batteries, about 5 kilos. So it is a massive drone that can go really, really quick. And you might ask yourself, what is the point of this? It seems a bit dangerous and very, very quick. If you imagine something like this, ripping around about 150 k's an hour, pulling 8 Gs, really, really difficult to see for the spectator. Whereas something like this, if we put heaps and heaps of LEDs on the side of it, then it's really, really visible for the spectator, and it's awesome fun to watch because people can see it without having to tune into the live video feed, and really, really awesome. The other great thing about these is the crashes are absolutely spectacular. So when you watch those motorsports, you want that other aspect to it. You want there to be a little bit of interest and excitement when you have crashes. When these things crash, they sort of explode into many chunks because there's just so much force behind them that it's really, really fun to see. They also make an absolutely incredible sound when they're flying around, particularly once they get up to that top speed of about 250 kilometers an hour. The other awesome thing that's emerging with these is if we fly a bit slower, these can fly for up to 8 minutes and carry quite a large camera if we want it to. So if we want to put a professional grade camera on this, but get all the acceleration and all the dynamic movement of our standard racing drones, then we're able to do that. We're able to put a full-size camera on there and get some really, really cool shots. Some great examples of this is following some drift cars around. So you might not necessarily be able to chase them around with something like this, particularly when they go down the straight. Whereas if you put a full-size camera on this that gets that really, really high definition footage, we're able to follow those cars around and get some really, really cool shots. So I'll now hand over to Luke to tell a bit about what actually makes these up and some of the materials that goes into producing these.
Cool, thanks Nick. I'll just make sure I'm on camera here. Beautiful. Look, so you've seen a lot of different quads. We've got different sizes, they go different speeds for a range of different applications. I guess starting from how do I build one of these and where do I get started? And the best way to start is the frame. So you pick your frame size. This is a 5-inch frame size, and that aligns with 5-inch propellers. And I guess almost every single racing quad that you'll see will be made out of carbon fibre. But carbon fibre is not the only material that we can use. The reason why we do use carbon fibre though, however, is it's very strong. I can throw this, I can step on this, I can send this into a tree at 160 k's an hour by accident and it'll probably come out okay. And very rarely do they actually break. Other options that we do have, however, are things like plastics. We use nylons. As you can see here, really cheap and really easy to make, covers to go around all the electronic aspects of the quad. I'll just bring this in a bit closer if you can see it. Let me know. Get down there. Yeah. Brilliant. Yeah, so you can see right there, there's quite some interesting little features there, the little RAF symbols. So this is something that we've actually made and designed to fit around our RAF team quads. I know Army and Navy have got their own unique designs as well, which is pretty cool. These are all designed with what we call CAD software, which you might have heard about. And then we take our CAD software, we run it through a slicing program for 3D printing, and that effectively, it's hard to see on the camera, but that slices this design out of a CAD file, that slices into many, many layers. You're talking a couple hundred layers potentially, and that allows us to put that into a 3D printer, which then follows those layers around and progressively builds up these models. So what we might do is we might head over to the printer. I'll see if Alex can follow me through. If not, we'll get a zoom in. Perfect. Great. All right, we're right here. So what we've got here, we've got our Team 3D printer. At the moment, it's just warming up to start a new print. We might actually see that start any second from now. So what this is going to do, this is going to actually start building, if you can see, something like that. And what's going to happen is, as you can see, it's going to just be basically tracking this plate around. It's going to progressively build and it's going to move up as we go, building our part. Now, something that I've got here, which I just made just a couple of days ago. So I've made this up in a computer-aided design CAD software package. I've now put this through my own 3D printer at home. And the idea behind this, it's a one-stop shop, one-piece frame, probably more for freestyle because it will break. But the idea I can use now is I'm now planning on putting a carbon fibre base on the bottom like that, very thin. We're talking 1mm thin compared to 5mm, which is more standard for these types of frames. And the beauty about this as well is if I feel like this design starts working quite well and I want to actually take this off and make it into a racing quad, I can actually make that thinner in my CAD software. I can then send these files to a carbon fibre manufacturer. They will then do something effectively like that, and I can actually build my own frame, which is pretty cool. It is quite cheaper to buy one that's already out there because you've got thousands of parts being made compared to just the one. But I suppose if you're really interested and you love doing it, it's definitely worth it. So what I might do now is we're going to go over to a table. We're going to have a bit more of a chat about, I guess, all the components. I think Nick's just setting up. We'll just get a thumbs up, he's ready. Perfect. And we're actually going to pull apart one of the quads and you'll see the frames and you'll see all the pieces. Before we go there, I'll just get Alex to get a bit closer into this 3D print here just to see that building up. Perfect. I guess before we move on, is there any questions you'd like to send through to our desk officer? He'll be ready to fire them back at us and we'll talk more. Thank you.
Okay, so thanks for that, Luke, telling us about sort of the physical components that makes up the drone. Now I'm going to be talking a little bit more about kind of the electronics that go into putting this sort of thing together. So, as Luke mentioned, you got the base frame, and then what we've also got is all the cool stuff that actually powers this. So starting from the inside, that thing there with all the wires coming out, this is what we call an electronic speed controller. So what its job is to get a signal from our flight controller and convert that into something that the motors like. So you can't just directly hook up a voltage to the motors. What you need to do is, because these are brushless motors, you need a very, very special type of signal in order to power them. And that's what these do. That's what this electronic speed controller does. The other thing it does is take the input from the flight controller, being a value between 1,000 and 2,000, and converts that into an actual throttle value. So as I said, these things, the main thing we're concerned about these is whether they're able to power the brushless motors that we like, but also what language they use to talk between the electronic speed controller and the flight controller. So it's something default that the language that talks between them. The other key thing that we care about with it is how much current that it can actually pull through it. So these motors will want to draw a certain amount of power each, and we need to make sure that this electronic speed controller is able to deliver that for us. And if it isn't able to do that, then, well, you get fire and it drops out midair, which isn't what you like. So you'll notice that this board here actually has all 4 electronic speed controllers in one. Now, we usually use this for racing drones because that way it's all contained and it's not vulnerable on the arms. But the downside to this is that if one of these burns up, then we have to replace the entire board. So initially what we started off with is actually individual speed controllers on each of the arms. And the downside to this, they're very exposed out on the arms there. So if we got a bent propeller, it can actually hit those and damage it. You also notice that this arm is pretty thin because it's a racing drone. So we don't actually have a lot of room to be able to put a speed controller on there and keep this thin profile. So again, moving back into the center so that all we have to run out here is just wires to feed the motors. The final consideration as to why we went to this is weight. So if we need to get thick cables to go out to each of the arms in order to deliver that power that we want it to, that takes up a lot of weight. And our whole aim behind this is to keep the weight as low as possible so we can squeeze every little bit of performance out of these. And so that's the main things with the speed controller. They're really, really complex bits of kit, but without them, this technology would never take off. So moving on, we've got the flight controller. So this is kind of like the brains of the entire thing. So it's sort of like your motherboard on your computer. So this is what takes in a whole bunch of different signals and then puts it out to various different bits. So all of the stuff when it's controlling flight or taking signals from your receiver, that's all done here, as well as a whole bunch of fancy other operations like monitoring battery, monitoring how much current is coming through, monitoring where it actually is in space. So on board here, some key components that we've got is the main processor, so that really, really big black chip there. We've also got what we call accelerometers and gyroscopes. So what they do is they let the drone know where it is in space. So basically, if it's flat, the accelerometer will lead level. If it's slightly tilted, that's what the accelerometer will pick up, how much tilt there actually is. And what the gyroscope then does is detect how much change is actually happening there. So the accelerometer can detect if it's on an angle there, but it can't detect how quick it's spinning. But the gyroscope, that's what's able to detect how quickly it's spinning. And that's really, really critical for racing drones because what we care about most is holding that angle. So if we're flying around and hitting an angle like this the entire time, we want to be able to hold that angle really, really well so we've got a consistent speed and we know what's happening. And that's the whole purpose behind the gyroscope, to keep that as flat as possible. The other really, really cool bit about this flight controller is it actually filters out a lot of the weird noise and signals that we might have coming through. So if you imagine if one of these propellers is bent, this thing's going to vibrate all over the shop. And you don't really care about those vibrations that much. You don't necessarily want the flight controller to constantly trying to adapt to all of those vibrations, because what you end up with is a drone doing that. And if we're trying to see through this vision and the drone's doing that, we're not going to be able to see where we're going, and therefore we're not going to be able to race very well. So the flight controller and the software involved disregards all of that, just goes, I don't really care about this vibration, so I'm not going to react to them. But if something hits like that and suddenly tilts the drone out of shape, then it will respond to that. It will bring it back up to the level that you last had, and so that we can keep flying straight for us. The other key thing about this flight controller is the fact that it actually doesn't do a lot of onboard processing. So we want the time between us putting an action in and the drone responding to be as quick as possible. So we don't really want the flight controller to be doing much thinking for us. So when we're racing around, the only thinking it does is holding that last angle. It has no idea where it is in space. It has no GPS, as I mentioned before. So all it really does is holds that last angle for us, and the rest is all up to the user. As I mentioned, this takes in a lot of data from a few different points. So you notice this thick bundle of wires here, that's connecting the electronic speed controller and the flight controller. So you've got one wire for each of the motors, as well as power, ground, and also signal. So the electronic speed controller is actually telling the flight controller what's going on. So how much current is it drawing, what speed are the motors actually going at. Moving on from there, we've got this little thing here that's wrapped up in heat shrink and got two little antennas. This is what we call the receiver. So when we've got a radio like this, we need to be able to we need a way to communicate between the drone and the radio. And that's what this little thing does here. So it's quite small, but even though it only weighs about 2 grams, we can still fly this out to about 1.5 kilometers. So really, really powerful for its size. You also notice that there's 2 antennas on here. The reason why there's 2 antennas is because this is such a critical link. We need to be controlling the drone at all times. What this smart little receiver does is it takes a signal from each of these antennas and decides which one is the more powerful signal, and it will go with that. If it sees this antenna is pretty weak, won't really care about this, but this antenna is really strong, it will go with that one. And I believe we have a question coming along.
Yes, we do. If I can change your camera. There's too many buttons on this thing. Oh, there we go. Here I am. Yeah, so we have a question here. How often do your components break or fail? I know for me, I break them a lot, but what about flying around and stuff? So
this all depends about how you actually design your components. So when it comes to racing drones, because we're pushing the very, very limit of what this technology can do, we actually find they break quite often. It also doesn't help when you've got not great pilots such as myself, and we hit obstacles at 80 kilometers an hour, they tend to break, unfortunately. So to give a bit of a figure, most components probably only last about a month if we're flying regularly. But if you go to a more freestyle drone where you're doing less risky stuff and not pushing the bounds as much, I've had a drone that's able to be able to operate without any errors for about 9 months. Hope that answers your question.
that's fantastic. We also have a follow-up question from that. So if we do break something, how quickly can we fix that? I'm not too great at it, but we know that Nick's a pretty good solderer, so can you expand on that a bit?
Sure. So it all depends on what the component is. So if you break something like that electronic speed controller, you'll notice that there's 12 wires coming off as well as this little plug. So this is going to take a little bit of time to replace. And this is where the design of these drones actually plays a critical part into it. Because if we're racing around and we've got 5 minutes between races, if we do break something, we want that to be replaced as quickly as we possibly can. So what you'll find is we often design our components so that that's possible. So one example is instead of directly soldering this big bundle of wires, we use a plug. For the flight controller here, because it's taking in a lot of inputs, then it takes a bit of time to replace, probably about 15 minutes. If we go to the camera, so the camera which is nestled up in that pod there, which unfortunately is a bit difficult to see, this is probably one of the most common components to break because it's up the front of the drone and usually we start looking at the wrong thing and hit it. Great thing about the camera is it's only one little plug and it's connected to the flight controller, so all I have to do is unplug it, unscrew the camera, put it back in. Unfortunately, I've got very, very well practiced at replacing that, so I can do it in about a minute now, but that is due to the loss of a lot of cameras. Hope that answers your question.
That was great. Thanks.
So while we're on the topic of the camera, as I mentioned, you'll notice that the camera's actually going into the flight controller. So that little wire there, that's what goes into the flight controller and plugs into the back of the camera. Now, a few of you might be asking the question, if the flight controller is just caring about my angle, why is the camera going into there? The reason for that is it's overlaying a whole bunch of information for us. So when you see the flight footage later on, you'll notice that there's a few figures on there, such as your main battery voltage, how much current. This is fully customizable by our pilots in the back-end software. And so we can put as much information as we want on there as possible or as little. So for example, if I'm racing around and I'm really tunnel vision focused on hitting that next gate, probably all I care about is how much battery I've got and how long I've been flying for. But those longer range drones that I was talking about, we probably more care about what my altitude is, how much battery I'm chewing per hour, how long I've been flying for, where I am in space, how quickly I'm flying. So that's fully customizable. And that's why the camera is going into the flight controller and all that information gets overlaid over the top. You also notice that the camera, tiny little lens at the front there, is actually really small. And some of you might be thinking, isn't this going to be absolutely garbage footage if the camera's that small? And you're right. The footage from these cameras isn't that great. The only purpose behind these cameras is to be able to show exactly where we're going. So if we're flying around, if it's facing back towards you, left is left, right is right, forward is back. Easy. But what if it's tilted like this? Looking at the way you are, if you hit left, it will do that. So that gets quite confusing. It's actually quite difficult to fly in this mode. So the camera along with goggles, allows us to maintain that orientation and be as if we're flying on board with it. Now, what makes that possible? This little thing here. So this is what we call a video transmitter. So this gets the signal coming out of the flight controller, which has overlaid that information for us, and then broadcasts to some FPV goggles. So these are the goggles here. Now, one of the things you might notice is that unlike our little transmitter here that has 2 antennas, this just has 1. And the reason for this is we want the time between the camera seeing it and us seeing it to be as short as possible. So we don't want anything interfering with that. If it's got to flick between 2 signals, that starts to interfere with us. And that's the reason why the footage isn't that great, is because it's that old school analog style, so that we get about 20 milliseconds between the camera seeing it and us seeing it. So as I mentioned, this little video transmitter spits out that video to be received by goggles. I believe we have a question.
Yeah, I was just going to add a bit to that. So we can play some video just for people wondering, what does this actually look like? So if I can get this live stream to work, there's a lot of buttons on the screen here. If I press this one, I'll let you continue on for a second, Nick, while I find this video. Oh, here we go. I think that is live. Okay, so this is from a race earlier.
Goggles
late
down,
last year.
thumbs
Air
up.
Force drone racing tournament. This has 4 pilots racing against each other.
We go live on the tone in less than 5.
So the pilots are about to start here. This is at basically footy oval. As you can see, this is what the pilots actually see while they're racing around. We have 4 pilots competing. I believe I was in the top left-hand corner. I didn't come across this race. I crashed out. But if you look carefully, you can actually see the drones in other people's video feed. Trust me, it's quite scary, especially when you're flying around a couple of $1,000 with a drone and some crazy drone. Not a great feeling. So we see in the bottom corner, Squish, one of the depth pilots actually crashed out and lost the video altogether. The blue screen death as such. And races only go for a minute or 2, depending on the main one is actually battery life. The video is there, it's popping up with low battery. See, okay, I think I'm close to that one. No. Might give it a second, and then flaps. Other drone racing pilots it comes in we like to banter around sometimes. Hopefully he's tuning into the live stream at some point. So hopefully that fills in any more information about what the drones actually look like from the camera feed. So I'll pass back over to you, Nick.
Yeah, thanks for that, Jake. So as you would have seen in that feed, that there's a lot of interference going on, and the video quality isn't actually that great. And as I mentioned before, we want that time between the drone seeing and us seeing it to be as low as possible, and that's the reason behind it. If we wanted to go higher quality, what that means is a greater time between the camera seeing and us seeing it. So the high quality digital systems at the moment sit at about 80 milliseconds between camera seeing it and us seeing it, whereas the analog is about 20 milliseconds. So you can see that's a really, really big difference. And we really want that time to be as low as possible. If you notice how quick our team pilot Dello was flying around, and then imagine the world champ who was able to do that track in just 9 seconds for a lap, he's really going to want that really, really quick reaction time. So that video is being received by goggles like this. So these are not VR goggles. Their only purpose is to receive an FPV signal, so first person view signal from a drone. So key point to this is inside there, you've got 2 little screens and you put this on your face. This gives a really, really immersive feel to it and removes any outside distractions. So if you're trying to fly just off a screen, then you'd have a whole bunch of stuff on the outside and it'd be pretty hard to concentrate. Whereas you put these on, all you see is the feed from the drone and it's really, really immersive, so you almost feel like you're flying. You'll actually notice if you ever go to a race, that a lot of the pilots land their drone are actually quite nervous afterwards. It's almost as if they've been flying a real aircraft. And that's a bit of the joke. It's the closest you can get to Red Bull air racing without being a professional pilot. And it feels just like you're flying. Really, really high quality screens in there, so it's awesome footage we get out. So this big red thing here, This is what gives the signal, receives the signal that the drone's putting out. So because it's analog feed, the great thing about it is anyone can tune into it. So it's like tuning into a TV station. All you need is the equipment on the ground side and you're able to tune into it because this receiver here doesn't actually talk to the drone, it's just sort of receiving it. So you notice here that there's 2 antennas. Now most receivers, what they do is similar to our little receiver I talked about before, is takes the signal from both of the antennas and decides which one is the better one. And then it will put that in for you. Most of the time what we do is we run one antenna which is very, very directional, so it can only take a pattern from a narrow path, and then one that can sort of take a signal from any area around it. But on this one here, you've got 2 that can take from anywhere area around it. And the reason for this is this receiver here is actually a really, really smart one. So what it does is it combines the 2 signals to make an even better one. And this is really, really useful for when we're flying in environments like around here, where there's heaps of metal, so the signal's just bouncing off everywhere. So we want to be able to pick the signal that's really, really good, but also combine the 2 together so we get a lot less interference in order to get that much clearer picture. So when we fly around later on, you'll notice that the interference is even worse than what you saw in that little quick video before. And the reason for that is because it's reflecting off all the metal, and this receiver does some really, really cool technology by combining those signals together and is able to get rid of a lot of that interference for us. But you'll notice that, unfortunately, there's no cheating the laws of physics, and we still get a lot of interference. The other one is, this actually operates on the same frequency as Wi-Fi. So these receivers do a lot of filtering, which is where you're disregarding a lot of that other signals. So Wi-Fi is bouncing around as different signals, and this receiver goes, that doesn't look like a video feed, let me get rid of that. Or when you tune into a specific channel, it will only look at that very, very specific channel. So it's like if there was a lot of people talking in a room and you're focusing just on one person's voice. And that's what this receiver is able to do, which is really, really cool bits of kit. I think we have another question, Jake?
Yes, we do have another question. There we go. The question is, what is the range of a video of a drone, or range of a control, or range of a battery?
Great question. So there's a lot of different parts to that. So it all depends on the equipment and how we've got it set up. So with this antenna here, we've got a couple of things. We can control how much power that's actually putting out. So typically we race on a power of about 25 milliwatts because we've got a lot of people competing against each other, racing next to each other. And so we don't interfere with each other, we go quite a low power. But if we're able to push that video signal up to about 800 milliwatts, we're able to actually go out to ranges of up to about 10 kilometers. Now the control link on this little small cheap one here, we can probably do about 1.5 kilometers. On some of the more advanced ones, which are quite common, that uses a different frequency, that can go up to 40 kilometers away.